Welcome to Talk Tensors. Today we're digging into some really interesting machine learning research, specifically a paper presenting a new neural network architecture that's, well, remarkably efficient.
That's right. If you're looking at ways to get top AI performance without needing, a supercomputer, this should be fascinating.
Absolutely. So the focus is on RAPFI. It's a network built for the game Gomoku.
And what's really grabbing attention is how RAPFI manages to outperform much larger networks. We're talking the usual suspects, CNNs, ResNets.
The ones that usually need hefty GPUs.
Exactly. RAPFI does well even against Codebook, which is a very strong open source AI, especially when you constrain the resources, like running only on a CPU.
And it's not just theory, right? This thing actually performed out in the wild.
Yeah, it ranked #1 on BotZone out of 520 agents, and it won the Gomoku 2024 championship. Real-world validation.
Okay, so that sets the stage. Our mission today is figuring out how. How does RAPFI pull off this high-level play with such computational frugality? We need to unpack the techniques and the context behind it.
Well, the paper kicks off by acknowledging how games have historically pushed AI forward. Chess with Deep Blue, then go with AlphaGo, AlphaGo Zero, Katago.
Right, those deep learning milestones.
But those milestones often came with a pretty steep computational price tag. Lots of GPU power needed. RAPFI's main aim, the researchers state, is different. Keep the accuracy high, but slash the runtime, especially when compute power is limited.
And Gomoku is the testbed here. 5 in a row on a grid. Simple rules.
Deceptively simple. With free openings, it's solved, technically. But add balanced opening rules, and suddenly the strategy gets incredibly deep. You need really precise board evaluation and look ahead.
Okay, so the paper points out a potential issue with standard CNNs for board games.
Yeah, a kind of redundancy. CNNs are great at patterns, but on a game board, one move only changes a tiny fraction of the input. Recomputing everything seems wasteful.
Ah, I see. So RAPFI's idea is different.
Fundamentally, it breaks the board down into local patterns, like small line segments, and then it pre-computes features for these patterns.
Pre-computes? Like calculates them ahead of time?
Exactly. This leads to their architecture called MixNet. It's lightweight, uses this pattern-based codebook for fast feature lookups, and crucially has an incremental update scheme.
Incremental update, so it only updates what changed.
Precisely. Minimizes computation when just one stone is placed. Perfect for depth-first search. They also added some enhancements to the network heads for accuracy, but we can get into those.
So key contributions are this pattern decomposition, the codebook idea, the incremental updates, and some specific network tweaks. Got it.
The paper then situates this work. It looks at other efficient network designs, things like MobileNets, Senet, Concom.
Techniques people might know for making models smaller or faster.
Right. But they argue RAPFI's approach, this pre-computation and incremental update, is novel compared to those more general methods. They also mention background techniques like depth-wise convolution, dynamic convolution, things that improve efficiency structurally.
And they also discuss search algorithms, I assume. You can't have a game AI without search.
Of course. They touch on Monte Carlo tree search, MCTS, which was huge for Go.
AlphaGo's engine, essentially.
And also the classic alpha-beta search, which has a long history in games like chess. The key thing is they evaluated RAPFI with both MCTS and alpha-beta.
Shows flexibility. And Gamoku itself has its own history of AI approaches.
Yeah, threat space search, proof number search, various techniques before the deep learning wave hit, largely inspired by AlphaZero. RAPFI builds on all this context.
Okay, let's dive into the methodology. How does MixNet actually work? Input is the board.
Yep, a binary representation, one hot encoded. Output is the policy, the probability for each possible next move, and the value win, loss, draw probabilities.
And the core pieces, again, are the pattern part, the codebook, the update mechanism.
And the lightweight heads for policy and value. Figure 1 in the paper lays it out nicely.
So breaking down the board, you said line segments.
Exactly. They look at lines of length, 11 in all 4 directions, horizontal, vertical, and both diagonal.
Why 11?
It seems enough to capture a 5 in a row plus some context on either side. They then use functions to turn these visual patterns into numerical features the network can process. An aggregation step combines features from the 4 directions.
And the codebook, how is that built? You can't store every possible board state.
No, that'd be impossible. Instead, they train a separate small network they call the mapping network. This uses special directional convolutions, think filters, specifically looking for horizontal, vertical, or diagonal patterns.
Oh.
This mapping network learns to extract the essential features from any given 11-length line pattern. Once it's trained, they run every possible 11-length pattern through it and store the resulting feature vector. That stored collection is the codebook.
So the lookup, when the AI sees a line pattern on the board during a game.
It doesn't need to run the mapping network again. It just looks up the pre-calculated feature vector from the codebook. Super fast.
That's the speed up.
Yeah.
And the incremental update builds on this.
Directly. When one move is made, only a few of those 11-length line patterns overlapping that square actually change. RAPFI identifies those changing lines, looks up their new feature vectors in the codebook, and just updates the overall feature map accordingly. It keeps an accumulator and adds the delta or change.
So instead of processing the whole board's features again, just update the bits that changed. Very efficient for search.
Hugely efficient, especially for depth-first search algorithms like alpha beta, where you explore sequences of moves one after another.
He also mentioned enhancing the final prediction parts, the heads.
Right, the feed-forward heads, they have a dynamic policy convolution. It seems to use global information from the feature map to dynamically adjust how it calculates the move probabilities, helps capture the bigger picture.
Interesting. And value grouping.
Yeah, they divide the feature map into like 3x3 chunks, corners, edges, center. They process these chunks separately using something called a star block, and then combine the results to predict the win-loss draw value. Gives a better spatial sense for the evaluation.
A star block. Sounds fancy.
It's just a specific sequence of linear layers and multiplications designed to add nonlinearity efficiently, boosts accuracy without much computational cost.
Okay, that covers the how. What about the experiments? How do they test it?
They needed data first. They generated a massive data set, over 30 million positions, using Codebook to provide the board state, the actual outcome, win-loss draw, and Codebook's preferred move, the policy target.
Using the opponent to train the challenger, essentially.
Kind of, more like using a strong existing AI to generate high-quality training examples. They trained 3 sizes of MixNet small, medium, large, and compared them to standard ResNet sizes.
Comparing parameters, FLOPs, speed.
Right, usual metrics.
Exactly. Table 1 in the paper has all those numbers. They use standard training techniques, atom optimizer, learning rate schedules, and they also employed knowledge distillation.
Where the smaller network learns from a bigger teacher network.
Precisely. They used a pre-trained ResNet as the teacher to help guide MixNet's training. Helps transfer some of the knowledge from the larger model. And the actual playing strength tests? MCTS and alpha beta.
Both. They used a tuned PCT variant for MCTS with some enhancements. For alpha beta, they used principal variation search with lots of standard optimizations like transposition tables and pruning, using the network's policy output to help order moves for better pruning.
So the results, did MixNet hold up?
The findings were pretty compelling. Looking at just the network predictions, MixNet learned the value win-loss draw really well, sometimes better than the ResNets. Its raw policy prediction wasn't always quite as good as the larger ResNets, though.
Interesting trade-off.
But here's the kicker. RAPFI's inference speed was orders of magnitude faster. We're talking hundreds or thousands of times faster, according to their Table 1.
Wow, okay.
So when they ran actual time-controlled matches, even if RAPFI's initial guess for the best move wasn't perfect, it could search so many more positions in the same amount of time.
Ah, the search compensates.
Massively. Figure 5 shows MixNet consistently beating the ResNet baselines by huge ELO margins, like 300, 400 points, which translates to win rates around 85–92%. The speed advantage was decisive.
And how did it fare against Codebook itself?
When combined with their advanced alpha-beta search, the MixNet-based RAPFI actually achieved around 400 ELO higher than the Codebook CPU version under the same limited resource conditions.
That's impressive, beating the thing that generated its training data.
It really is. Interestingly, the largest MixNet didn't always perform best with alpha-beta. They speculated the cost of updating the larger codebook might become a factor there, but the medium and small sizes were extremely strong.
They do ablation studies, removing parts to see what matter.
Yes, Table 3 covers that. Removing the star block or value grouping hurt the value prediction accuracy significantly. Removing the dynamic policy convolution hurt the policy prediction.
Makes sense. It confirms those design choices were important.
Exactly. And it showed MCTS was more sensitive to policy accuracy, while alpha beta relied more heavily on accurate value evaluation, which aligns with how those algorithms work.
So to wrap up the paper's findings, RAPFI, powered by MixNet, is super efficient. The pattern decomposition, codebook, and incremental updates are key to its speed. The specialized heads help maintain accuracy. And it demonstrably outperforms larger networks and even strong Gomoku AIs like Codebook when compute is limited.
That's the gist of it. The BotZone ranking and Gamoku win are strong evidence. It really showcases the potential for compact, specialized networks when evaluation speed is paramount. They do mention limitations like the network being relatively shallow and potential scaling issues, but the core achievement is clear.
It's helpful to place this in historical context, too. AI in games has gone from rule-based systems to deep learning monsters.
Often demanding more and more compute, Gamoku's been a useful middle ground complex, but not Go-level intractable initially.
And search evolved from minimax and alpha-beta pruning to MCTS.
Driven largely by the Go breakthroughs. Deep learning, CNN specifically, boosted performance across the board, but brought those computational costs. RAPFI feels like part of a broader trend towards efficient ML, needed for mogul edge devices.
But with a very domain-specific twist here, it's not just general efficiency tricks. It's deeply tied to Gomoku's structure.
Absolutely. While there were other efficient Gamoku attempts, this codebook and incremental update combo seems unique and highly effective.
So the clear, non-repetitive takeaways. The pre-computed codebook is a massive speed-up. The incremental update is perfect for game search. Lightweight mixnet achieves accuracy rivaling bigger networks for less cost. The special heads add accuracy efficiently. And domain-specific design really shines under resource constraints.
Couldn't have said it better. Beating a strong AlphaZero style agent like Codebook really underscores the point.
What about real-world implications beyond Gamoku? Could these ideas travel?
I think so. The core concepts, decomposing input, pre-computing local features, efficient updates for incremental changes could be relevant elsewhere. Maybe robotics, where sensor data changes locally, or certain resource management tasks.
Anywhere the input isn't completely reshuffled every time step.
Right. The idea of distilling knowledge into fast lookups could be useful for embedded systems or mobile apps needing real-time AI. It pushes towards making sophisticated AI more deployable on everyday hardware.
It suggests that by exploiting domain structure, maybe we can find similar efficiency wins in other complex ML areas, not just games.
It's a promising direction, definitely.
Which brings us perfectly to our novel notions segment. Where could this research lead next? Got any ideas?
Well, one obvious thought is, how generalizable is this pattern codebook approach? Could we apply it to other board games, maybe Hex or Lines of Action, games with different connectivity, different winning patterns?
So could you define different local patterns relevant to Hex, like connection paths, build a codebook, and get a super efficient Hex AI?
That's the question. It connects efficient design with domain knowledge. RAPFI success is encouraging, but the type of pattern and the design of the mapping network would need to be fundamentally rethought for a game with different geometry like Hex.
The challenge would be identifying the right local patterns for a completely different game.
Exactly. But the potential impact is huge. Resource-friendly AIs for more strategy games. The overlooked bit might be just how tricky designing that mapping network could be for really diverse pattern types. Probability? Moderate, I'd say. Depends heavily on how well the core idea transfers.
Okay, idea 1. Generalize the pattern codebook approach. What's idea 2?
What if we used meta-learning to automatically figure out the best patterns and the best network architecture? Instead of us hand-designing lines of length 11...
A system learns which local configurations matter most for Gamoku, or maybe even for any given game, and designs a mixed net-like architecture around them.
Precisely. You could leverage AutoML, neural architecture search. The hand-engineered success of RAPFI gives a target to beat.
That feels ambitious, but powerful. It could make designing these efficient, specialized AIs much easier, potentially opening it up for niche domains without needing deep human expertise in both the domain and architecture design.
The potential impact is democratizing efficient AI. But the overlooked parts are, well, the meta-learning itself can be computationally expensive, and would the learned patterns even be interpretable? We might lose some understanding.
Probability for this one?
Lower in the short term, I think. Depends on advances in meta-learning making it more feasible and efficient. But definitely thought-provoking.
And of course, standard disclaimer. These are speculative ideas just for sparking discussion.
Absolutely. Fun to think about, though.
Okay, so recapping our deep dive on RAPFI, an impressive demonstration of efficiency in Gamoku AI through clever architecture, the pattern codebook, incremental updates being key. Definitely check out the paper if you want the full technical details.
So worthwhile read.
And for you, our listener, the final thought. How might these principles we discussed, efficient, domain-aware AI design, apply to the machine learning challenges you might be tackling right now?
Thanks for joining us on Talk Tensors for this exploration. We hope it gave you some valuable insights into efficient ML.